Okay, Steve. So our first speaker this afternoon is Carsten Thomassen, and he's going to speak about chromatic roots and the second Hamilton cycle.
Thank you very much. I would like to spend the first few minutes on the first question, the following question, which I'm sometimes asked: does there exist a list chromatic polynomial? So I should say what list coloring is. I don't know if this is of interest in physics, but it has become very popular in graph theory. List coloring is the following generalization of ordinary coloring. You have a graph, and for every vertex you have a list of available colors. And then you want to color the vertices of the graph such that every vertex gets a color from its list. And as usual, neighboring vertices should have different colors. So here is an example. Suppose you have the following graph. You can see a list at every vertex. Can you list color in this case? Yes, you can give this. You have to give this the color 1 or 2. You can give it color 1. Here you have to use color 2 or 3. You can use 3. Here you can't use 3 because that's already used here, but you can use the color 4. And here you can then give it the color 5. So in this case, it is possible to list color. So sometimes it's possible, sometimes it's not possible. And we say that a graph is k-list colorable if the list coloring is always possible, provided all the lists have at least k colors. So every vertex should have at least k available colors. If a list coloring is always possible, in that case we'll call it k-list colorable. Some people also call it k-choosable. And of course this generalizes ordinary k coloring, because ordinary k coloring is just a k-list coloring when all the lists are the same. For example, 1, 2, 3 up to k. Now the intuition says that if the lists are far apart, then it will be easier to color than if the lists are almost the same, if the lists are compact. But that intuition is false, as we can easily see. This is a standard example. The graph here is clearly too colorable. You can give the vertices on the left side color 1 and the vertices on the right side color 2. But if you look at these lists I have put here, then you have 2 colors in every list, but a list coloring is not possible, because if you look at the left side, if you color these vertices, you cannot use the same color for all of them, because these 3 lists have nothing in common. So there must be 2 that have different colors, for example 1 and 3. But then you have a problem on the right hand side. There'll be one vertex that cannot be colored, because this vertex has only available colors 1 and 3, but they are already used in the neighbors. So list coloring is more complicated than ordinary coloring. So is there a list chromatic polynomial? It's not so obvious how to define it. One way is to do the following. Instead of specifying the available colors, we might also specify forbidden colors. We might say that this vertex is not allowed to have color 2 and 5, this vertex is not allowed to have color 9 and 13, etc. And then you could say that the available colors are 1, 2 up to k minus the forbidden colors. And now you have something that depends on k. And therefore you can begin to talk about the number of such colorings, and is that a polynomial? And that turns out to be a polynomial, because well, you can just do deletion contraction. And when you contract an edge, if you contract an edge uv into a vertex w, then you let the forbidden colors here be the union of the 2 sets of forbidden colorings. And using that, you prove, as usual, that this is a polynomial for k large, only for k large. The beginning of the induction is the graph with no edges, and that's easy to investigate. So this is a polynomial.
Should again follow from this Potts model equivalence, because you just fix, this is fixing boundary conditions. You fix some colors outside, and now you have partition function, which is clearly polynomial.
But again, it's funny, but it's a polynomial for large enough.
Yes, it's only for large enough. It's not a polynomial for small values of k, only when k is larger than the largest forbidden color you can see.
You're assuming that the set of forbidden colors is finite.
Yes,
That's crucial.
Yes, that's crucial. Yes, that's right. Thank you. So it would be interesting if if this function has any meaning, any applications. I don't know if it has any applications. The only interesting thing I can say about it is that it's a polynomial. Here is another approach, which I think is maybe more interesting. So we can look at all list assignments with k colors in each list, and then we can take the smallest number of list colorings. So again, you look at all list assignments such that every vertex has precisely k colors. Then you look at the number of list colorings and you take the minimum for all list assignments. That's another thing we might think about, and that's a complicated function. I call it the list color function. For example, let's go back to K33. If you look at the ordinary chromatic polynomial, the number of 2 colorings is 2. You might say it's only 1, but then you can commute colors and that gives you 2. And as we have seen, the number of 2 list colorings need not be 2 list colorings. So this minimum is 0. But then if you substitute for, if you put lambda equal to 3, you will have some list colorings. I don't know how many. I suppose we could work it out, but this turns out to be complicated even for small graphs.
So one application is radio broadcasting, where the different broadcasting stations have different frequencies.
Yes.
Sets of frequencies.
Yes, that's right. That's also sometimes mentioned as an application of list coloring, and other scheduling problems are mentioned. Well, would you call that physics? Is that physics? Maybe it's physics.
Engineering.
Engineering, yes. Yes, but it would be nice if there are some more applications of this polynomial. So if you look at the ordinary chromatic polynomial, we have this jumping situation. If you substitute, if you put k smaller than the chromatic number, we know that the number of colorings is 0. So the chromatic polynomial is 0 up to the chromatic number, and then it jumps, it goes to k factorial because we can commute colors. Does something similar happen for this list color function? I don't know. Is it possible that this function can have the value 1 for some k greater than or equal to 3? First I asked the question also for 2, and then somebody came up with a counterexample, Esperet and Goncalves. They proved that you may have this, and even this is not completely trivial. Let me just show the graph showing that a 2 list colorable graph and a list assignment such that you only have 1 coloring. But can this be achieved also for 3 and 4, etc.? We don't know. Another thing, here is a very dangerous conjecture, so I won't call it a conjecture, just a problem. Suppose that the list chromatic number is strictly greater than the chromatic number, as we saw for K33. Is it then true that the number of list colorings will not only be positive, but even an exponential function if you let k be the list color number? Might that be possible? This sounds wrong, but there is a little bit of evidence for this, namely the following. I proved that if you have a planar graph, we know that a planar graph is 4 colorable, but it's not always 4 list colorable. It is always 5 list colorable. And if you look at the number of list colorings, 5 list colorings, that's always an exponential function. It's always greater than n over 5. So will this phenomenon happen for all graphs? Probably not, but I don't see a way of disproving it. We know that it's hard to find the chromatic number. It's NP hard or NP complete. And therefore, of course, it's also hard to find the chromatic polynomial. But for a fixed graph, we can at least compute the chromatic polynomial in finite time by deletion contraction. Not a good algorithm, but it is an algorithm. Well, here is a theorem saying that we can do the same for the list color function. The list color problem may be harder than in NP. It's not clear that list coloring is an NP or co-NP. But we can compute this polynomial. Given a graph, it can be computed in finite time. And the reason is that this function turns out to be the chromatic polynomial for n large. So if you give every vertex k available colors and ask for the number of list colorings, it's at least as big as the number of ordinary colorings, but only for k large. We know it's false for k. We know it's false for k small, but for k large, it is at least the same as the number of colorings, and therefore this might have some interest.
It's k to the 9th, n to the 9th.
N to the 9th, yes. Yes, so the number of colors should be at least the number of vertices to the 9. This is
Can you
proper.
say a word about how you get 9 then?
Well, it just comes out from the proof. Maybe I could do 8 if I'm, but I can't put a linear function here. That would be nice if one could. That I can't do. Maybe I can say just one transparency about the proof, and then I'll go on to roots of chromatic polynomials. We know that the chromatic polynomial looks like this. It starts with k to the n, where n is the number of vertices. Then we know the coefficients are alternating in signs. And the first little thing I proved was that this list color function is at least k to the n minus a1 times k to the n minus 1. a1, by the way, is the number of edges of the graph. Now, this is not terribly interesting. For k large, it's not so interesting because this is strictly smaller than the chromatic polynomial. And for k small, it's also not interesting because the right-hand side is negative. But at least it is a little bit of a relationship between the list color function and the chromatic polynomial, because these are the first two terms in the chromatic polynomial. And this holds for all values of k. But then here comes something which is a little more interesting. And that was the crucial thing in the proof of this n to the 9 theorem. Suppose that all lists have k colors, and you have two neighboring vertices where the lists are not the same. Actually, the symmetric difference should be rather large, namely n to the 4. Then the number of list colorings turns out to be at least the polynomial, which consists of the first 3 terms in the chromatic polynomial. And this is nice because this is strictly greater than the chromatic polynomial for k large. So that's the idea. That's the idea in the proof. The rest will be about ordinary chromatic polynomials. I'm going to talk about roots, and here is something Bill also mentioned in his talk. If you have a connected graph with n vertices, then deletion contraction implies these inequalities for lambda smaller than naught, and also we have something for lambda between 0 and 1. In other words, the chromatic polynomial behaves like a tree if for lambda smaller than 1, except that the sign here between 0 and 1 also depends on the number of blocks, I think. So for lambda smaller than 1, the chromatic polynomial is not so interesting if we just are interested in roots, because there is only 1 and 0. And then this beautiful result by Bill, this 32 over 27 result, which is strange because 32 over 27 is such a nice number. I remember I once asked Bill, what is this number? And he just smiled. And Bill also proved that it's best possible. He found graphs with chromatic roots arbitrarily close to 32 over 27. One way to formulate this is that we have these zero-free intervals. We have 3 zero-free intervals. And then, of course, the natural question arises, are there others? And I'll do this quickly because Bill has already told us about it. There is a beautiful book by Jensen and Toft on coloring, and they asked, are there other zero-free intervals? And there are not. These are the only zero-free intervals. The chromatic roots are dense in the interval from 32 over 27 up to infinity. And I would like to say a little about the proof of this. The proof consists of some reduction formulas and then some elementary analysis. And the reduction formulas are the following. If you take two graphs and paste them together in a vertex, then the chromatic polynomial of the resulting graph is just the product of the two chromatic polynomials divided by lambda. And you have a similar formula if you glue two graphs together along an edge, and you can generalize this to arbitrary complete graphs. If you paste two graphs together in a complete subgraph, then you can factorize the chromatic polynomial. You can also glue two graphs together in two vertices which are not joined by an edge, and then you also have a reduction formula. It doesn't really matter what it says. The important thing is that we have a formula for this. So these are the only reduction formulas which I use in the proof. Then some elementary things from analysis. If you have a negative number b and a positive number a, and the ratio is irrational, then you can look at all integer combinations of these two, and you get a dense subset of the real numbers. And this actually also holds if you just restrict the coefficients to be natural numbers. That's an easy exercise. I mean, if you have no restriction on S and T, it's a very easy exercise, and well, it's also easy to prove that you can choose S and T in the natural numbers because A and B have different signs. And then you can translate this to multiplication using logarithms, and you get what I'll refer to as the ABC lemma. If you have a number A greater than 1 and a number B between 0 and 1, and now we have to assume that log A over log B is irrational. Then the set of all these numbers, A to the S times B to the T, form a dense subset of the positive numbers. And here I have formulated it in this way for every C and for every epsilon. You can find a number of this type which is between C and C plus epsilon. Therefore I call it the ABC lemma. And we can also prescribe the parity of S and T. If you want both of them to be even, that's okay. If you want S to be even and T to be odd, that's also okay. So this is very elementary. And then comes a graph result which is used in the construction. This is a strange result, and I will call this graph lambda node strange if lambda node is a real number greater than 1, and if the graph has an edge E with the following strange property. I'm going to contract the edge E, and then I'm going to see what happens with the chromatic polynomial in lambda node. The chromatic polynomial may go down, but this inequality says that it does not go down too much. So this is just a technical condition. Then another technical condition, if lambda node happens to be greater than 2, I will assume that these two numbers have different signs. When you contract the edge E, I'll assume that the chromatic polynomial changes sign from positive to negative or from negative to positive. Well, if this is the case, if we have such a graph with such an edge, then the following holds. For every positive epsilon and for any two numbers close to lambda node. So you take any two numbers, lambda 1 and lambda 2, close to lambda node, then you can find a graph H such that its chromatic polynomial in lambda 1 and in lambda 2 have different signs. And if they have different signs, then somewhere in between they will be 0. Somewhere in between we'll have a root by continuity. And
H is built from G naught. How?
Yes.
Oh, that's the next slide.
That's the next slide. Yes. So now comes the construction. Now comes the construction, like Alan showed us his constructions in the for complex roots. So here are the constructions for the density of the real roots. Here you take the strange graph and you take S copies of it. Here is this strange edge E, and then you take T copies of the 4-cycle. And one of the edges you call E, and then you take all these graphs and paste them together along the edge E. So you get the following graph. When you have done that, you delete that edge which you used, and then you call the resulting graph HST, and this graph will do the trick. Just one transparency why this can be done using the ABC lemma. You don't have to read this in detail. If you take the chromatic polynomial of this graph I've just constructed, then you can write it in the following way using the reduction formulas. This doesn't look nice, but the important thing is that you have a number here which we call C, and you have a number here to the power S and a number here to the power T, and we call these numbers in here A and B. And then by the ABC lemma we can choose S and T such that this number is close to 0. And also I can prescribe the sign of S and T. But it just occurs to me that where is lambda node? is lambda naught? What happened with lambda naught? It seems to be lambda naught minus 1. There must be an error in this. Well, I'm a little worried about this. I would have liked this to be minus lambda naught. Yeah, I'm sorry, there must be a mistake here. I'm sure this should be minus lambda naught. Well, anyway, the construction gives us the following, that we can, with the same S and T, the same S and T, but now with distinct. Well, if you look at this, just this expression, then we can make this close to 0. And we can also prescribe the signs S and T. And then with some more analysis. For some value of S and T, you can make this positive, and for another value of S and T, you can make this negative, but close to 0. Close to 0. That follows from the ABC lemma. And that's not what we want, because we are using different pairs of S and T, but then with some additional analysis, we can use the same S and T, but then for different lambda 1 and lambda 2 close to lambda naught, we can control the sign of this function. That takes some extra analysis. Yeah, I'm sorry about this, because it seems that I have made an error here, and I don't see what exactly is wrong, because I don't see the lambda naught here. That's the problem.
Carsten, if I could just make a quick comment.
Yes.
Can you put back your previous slide showing the graphs?
Yes.
If you look at G0 and C4 and delete the edge E, then
Yes.
in both of those cases what you have is a graph with two distinguished terminals, okay, which I will just think of in the electrical circuit analogy as a black box with two terminals. And then you're putting all of these black boxes in parallel. Now, from the point of view of the multivariate approach, where the edges get weights, in your case all the weights are -1, but nevertheless any black box with two terminals is equivalent to a single edge with some weight V effective. I showed it for you for series in parallel, but it's true any black box is equivalent to some V effective, which is a rational function of the V's inside and Q. And so you've constructed two black boxes so that putting them in parallel, they push in opposite directions. One of them has 1 plus V bigger than 1 in magnitude, and the other has 1 plus V smaller than 1 in magnitude, the V effectives, so that putting them together in parallel, you can get a V effective going anywhere, basically.
Yes.
And that's,
Yes.
I think that's the quote explanation of your proof in the multivariate language.
Yes.
You're using these two terminal black boxes cleverly chosen.
Okay, that's a nice way of looking at it.
So one of them is a 3-path, and the other
Yes.
is G0 with
A strange graph. Yes, yes, thank you. So in order to apply this, we have to find these strange graphs. And there were two conditions in the definition of a strange graph. There was a contraction condition. If we contract an edge, the chromatic polynomial is allowed to go down, but not too much. And then there was a sign condition if lambda naught is greater than 2. Let me first use it in a, you might say, in a negative sense. Let's first have lambda naught smaller than 32/27. Then we know by Bill's result that we can't construct graphs which have zeros. What that means is that this inequality can never be satisfied. This inequality can never be satisfied. So this means that the chromatic polynomial will always be bigger than what you get when you contract an edge. So this gives a way of proving that the chromatic polynomial is at least something for lambda smaller than 32/27, and you get the following inequality for lambda between 1 and 32/27. The chromatic polynomial of any graph will be greater than this. No condition on connectivity or anything. And this is best possible in a strong sense, because what you have here is the chromatic polynomial of a tree. And so if you let G naught be a tree, you have equality here. So you cannot improve on the right-hand side. And also the number 32 over 27, you also cannot improve on that one, because we know that the chromatic polynomial can go down and become 0 immediately after 32 over 27, and this function doesn't. So this is an inequality for the chromatic polynomial in this little interval between 1 and 32 over 27. And by the way, this inequality is true for all connected graphs, also when lambda is smaller than 1.
That G0 there is any G0.
That's any G0 with no condition. The beginning of the induction, I suppose, would be the graph with no edges. And that satisfies this in this little interval, because the chromatic polynomial is lambda.
G0 should be connected.
No, I don't think so. I don't think so. I think this is even more true if it's disconnected. Because if you look at the empty graph with no edges, then you have lambda to the n, and that's certainly bigger than this, isn't it? Should this maybe be n minus 1? Yeah, this is probably a misprint, yes. Yes. But if you want to have this inequality for all lambda smaller than this number, then you have to say connected.
Yes.
Because between 0 and 1, it would not be true if you don't say connected, because lambda to the n becomes very small, close to 0.
Oh, yeah. If you consider disconnected case, in general, you can put alpha to the power of number of concurrent.
Yes.
Number of concurrent.
Yes. Yes.
N
That's
minus
right.
C.
That's right. Yes. Okay, so this was an application in a negative way, but now let's go to the construction. If we look at complete graphs, are they strange? Well, for some values of lambda, yes, and it's easy to decide because we know what the chromatic polynomial is of the complete graph. It turns out that the sign condition is true for lambda smaller than m minus 1. M is the number of vertices of the complete graph, and the inequality, which I mentioned, is true for lambda smaller than m half. This is just a matter of looking at the polynomials for the complete graphs. So this means that the complete graph is lambda naught strange for lambda naught in this interval.
Is that an m minus 1?
Oh, here I should say maybe m minus 1. So either there is a misprint here or here. But I think let's... yeah, I think the misprint is here. Yes, it is. Because if you start with a triangle, if you start with a complete graph as a triangle and do the construction I did, then you get graphs of this type. You can see triangles on the left side, triangles minus an edge. And the density result says that the roots just of these graphs are dense in this interval between 3/2 and 2. So 3 is the number of vertices of the complete graph, and here we have m minus 1. 2 is 3 minus 1, so it is m minus 1. Let's go on with the complete graph on 4 vertices. That is strange in the interval from 2 to 3. And you get graphs of this type, and as you can see, they are planar. Let's go on to K. So this was K3 I used, this was K4 I used, K5 is using here. Now we go to non-planar graphs, but the roots are dense in the interval between 5/2 and 4. So if you take all these and combine them, you get roots in the interval from 3/2 up to infinity, because you see these intervals I've mentioned here, they overlap, fortunately. It's very fortunate that they overlap, because that's what gives the density result. But only from 3/2. We want to go all the way down to Bill's constant. So I tried K23, and that's strange in the interval from 1.36 up to 3/2. Then I looked at Bill's graphs, and it turns out that they are strange in the interval between 32 over 27 up to this number, 5 minus root 5 over 2, and that's 1.38, etc. And fortunately, that is bigger than this. So that does it. That does it. So that was the density result. Let's look at particular roots. There is the 4-color theorem, which says that 4 can never be the root of a chromatic root of a planar graph. And of course, one might try to prove the four-color theorem by proving this. I mean, this is a corollary of the four-color theorem. It would be nice if one could go the other way around, first prove this and then have the four-color theorem as a corollary. And this was in fact tried. Tutt tried this, and he came somewhat close. He proved that if you take a planar graph and you look at the chromatic polynomial's value in 5 plus square root 5 over 2, then that's always positive. And this number is 3.618, etc. So it's not terribly close to 4, but at least it's not too far either. This is not the golden ratio. I think this may be what Tutt called the silver ratio. He had a number which he called the silver ratio, and I think it may be this one. Then Bill already mentioned Birkhoff's and Lewis's result, and Alan also did in his talk. They proved that for lambda greater than or equal to 5, the chromatic polynomial is always positive, and they conjectured that this is true for lambda greater than or equal to 4. And this was also mentioned by Bill, a possible conjecture. Well, Bill said that I conjectured it, so maybe I should say that it's a conjecture. The chromatic roots of planar graphs consist of 0 and 1 and a dense subset of the interval from 32 over 27 and up to 4.
Does conjecture mean you guess that it's true?
I don't remember. But I certainly thought of this, and I probably also mentioned in the paper. I don't remember if I called it a conjecture or if Bill said that. Well, let's say that it's a conjecture. It has been around for some time now. So
everybody should be allowed. Everybody should be allowed only finite number of conjectures.
Yes. Do we have an upper bound?
But Hadwiger already made it infinite number.
So one thing we might try to, so we have the two interesting intervals, the interval from 3 to 4 and the interval from 4 to 5, and we can't do those. But we might try with an interval of this type. Can we prove that the chromatic roots are dense in this interval for some very small value of epsilon? And similarly, you might also try what happens very close to 5. Can we prove that the chromatic polynomial is always positive there? For some fixed epsilon, if you let epsilon depend on the graph, of course it's true by the 5-color theorem, but this should be a universal constant epsilon. And then close to 4, Gordon Royle has proved that there are chromatic roots, and I suppose that he will tell us more about that later on. The results so let me ask the following question. Which information does the roots give? If we know all the roots, then of course we know if we know all complex roots, we know the chromatic polynomial. But so what happens if we just know some of the roots? Does that give some information? And it does. If 1 is a root, well, we can conclude that the graph has an edge, because this means the number of colorings in one color is 0. So the graph has an edge, and you can't say more because you have if and only if here. And the same with 2. If 2 is a root, the graph must have an odd cycle. If 4 is a root, it must be non-planar. So this is a hard theorem, and the two other things are trivial. And if 3 is a root, then either the graph is non-planar or it has a triangle by Grütz's theorem. But these results are not really about the chromatic polynomial. These are combinatorial results which have been translated to the chromatic polynomial. It would be nice to go the other way around. Use the chromatic polynomial to say something about graphs. And this leads me to the following provocative question. We know that the chromatic polynomial was invented in order to study the chromatic number of graphs. But I don't think it has been very successful for that. So let me ask the following question. Does there exist some class of graphs for which the chromatic polynomial can be found or estimated using the chromatic polynomial? And it should be in an easier way than by combinatorial arguments. Just one single graph. I don't think we have one single example where the chromatic polynomial turns out to be useful.
So by using the chromatic polynomial, you might mean evaluating it at some non-integer value of t.
Maybe, yes.
Lambda.
Yes. Yes, just in some way. I mean, can you?
Because evaluating it in integers is too easy. You learn the chromatic number by evaluating it in integers until you find a non-zero value.
No, what I mean is that can you, for example, if you want to prove the four-color theorem, can you do that using chromatic polynomials instead of using the combinatorial reductions? That's what I mean. I mean, are they useful for finding the chromatic number? The chromatic number is difficult. We would like to have tools. Is the chromatic number, the chromatic polynomial such a tool? And I don't think it is. I mean, we have not a single example where the chromatic polynomial is used to compute the chromatic number.
Conceivable that it might be you could use it to prove Tutt's five-law conjecture. We sort of have some analytical proof of Welch's conjecture. That's the only thing I could hope for.
Yes, yes, of course. And then Tutt's five-law conjecture will say that this is a five-color theorem for planar graphs, and then you have the chromatic number. Yes. But I think I said easier. Easier than by more direct arguments. There are short proofs of the five-color theorem. So of course you can find some proofs of something, but what easier proofs than?
Well, Bill answered the dual question to yours concerning the flow polynomial. That a non-trivial conjecture about flow number might be a corollary
and is that
theorem about the flow polynomial.
And is that easier than by direct arguments?
Well, it's conjecture, so this is a hypothetical proof using polynomials.
Okay, but that's interesting. That's interesting. What about non-integer roots? Suppose you have a chromatic polynomial which has this as a root. Can you then conclude anything about the graph? Is there any conclusion? Such a graph does exist because this number is a little bigger than Bill's number, 32 over 27. So there are such graphs. Can we derive any information from this? And we can. We can conclude that it has no Hamiltonian path. and I think this is probably not useful for deciding if there is no Hamiltonian path. But from a philosophical point of view, I think it's interesting because it means that if you know everything about colorings of a graph, so you know so much that you know the chromatic polynomial, then in some cases you can make conclusions about Hamiltonian paths. The four-color problem, when that was formulated, there was another conjecture by Tate saying that every cubic planar graph has a Hamiltonian cycle. And the reason this was interesting was that if you have a Hamiltonian cycle, a cycle going through all vertices in a cubic planar graph, then you can easily four-color. You can color the interior with two colors and the exterior with two other colors. So this is an example where some Hamiltonian knowledge will give you coloring knowledge, but here's the other way around. Coloring knowledge may give you Hamiltonian knowledge. And this is, in some sense, best possible because there does exist a graph which has a Hamiltonian path and a chromatic root of this type. And the only difference between these, what you see here and here, is this 1 and 2.
Those numbers must be algebraic numbers, and so they tell you because
this need not be algebraic.
That one is not.
This one is algebraic, but this one is not algebraic.
Right, that's just a number you've written down.
This is just a number. You are allowed to continue this a finite number of times, and then I would like to continue the rest. But you can continue this. You can continue this. Yeah. No, I think actually, no, you're allowed to. I'm sorry. You're allowed to continue this as much as you. I take it back. You're allowed to continue this yourself as much as you wish, and it's still true what I'm saying.
Because there exist graphs with roots that are dense in 3227 to infinity. So you write as many digits as you want, and then you invoke your theorem to find a graph with a root near there.
Yes, but the only thing I'm saying now is that it has no Hamiltonian path. So if Norman gives me this graph, he just shows me he doesn't even have to show me the graph. If he just shows me the chromatic polynomial and shows me this root, then I tell him your graph has no Hamiltonian path.
So if I give you a graph and it's chromatic polynomial, can you decide whether the graph is Hamiltonian in polynomial time?
No, I can't even do it in infinite time. Because you look at a tree. Look at a tree. All trees have the same chromatic polynomial. Some have a Hamiltonian path, some don't. So it's impossible to, in general, say if a graph has a Hamiltonian path.
No, but I'll give you the graph.
Yes.
I'll give you the graph.
Oh.
With the chromatic polynomial.
Oh, you give me
If
both.
the graph is a tree, I can just.
You are so
check whether
kind.
it's a path or not.
You're so kind to compute the chromatic polynomial for me.
No, you get the input is a graph together with its chromatic polynomial.
Okay. Can I then decide Hamiltonicity? Of course, if it's a tree you give me, I don't even have to look at the chromatic polynomial. So that's a good question. I doubt it. I doubt it.
So you say you have a quick witness for non-Hamiltonicity, but not necessarily the reverse.
That's right. In some cases, it's only in some cases this works. Because for this one, it doesn't work. I mean, if you look at this one, it may have a Hamiltonian path, it may not have a Hamiltonian path. So if this is the root, then I'm stuck. I can't decide. Then I can't use the chromatic polynomial, so probably the answer is negative. But it nevertheless is an interesting question because you're giving me something which is in p hard. And if I'm allowed to use something which is in p hard, I'm in good shape. So it's still an interesting question. Let me say how I could say this. It comes from the following theorem. If you have a chromatic root smaller than this number, 1.29, etc., then it has no Hamiltonian path. And the number I have here is best possible. And what is this number T naught? Well, there's an explicit formula, and it's the root of this polynomial. And this polynomial is not a chromatic polynomial. Maybe I can say a few words about the proof of this and how I came to this theorem. So if you look at Bill's graphs, Bill described them. They all have the property that you can delete a small number of vertices in such a way that you get many connected components. So they have what we call low toughness. And if you have a graph with a Hamiltonian path, that has good toughness. Because if you look at a Hamiltonian path is a path going through all the vertices. If you take, for example, 5 vertices away, you don't get more than 6 connected components. And Bill's graphs do not have that property. He can take a few vertices away and get hundreds of components. So therefore I thought that maybe it would be interesting to look at a Hamiltonian path. And I tried to prove a theorem of the following type. I took any number between 1 and 2. Any number S naught between 1 and 2, and actually I should say it should be greater than Bill's constant, 32 or 27, otherwise what I'm saying here is not interesting. And then I would like to prove the following statement. Suppose you have a graph and it has a chromatic root smaller than S naught. I would like to be able to conclude that it has no Hamiltonian path. When I wrote this down, I wasn't even sure if there would be a theorem of that type, and I would settle for any S naught. So Alan defined a theorem to be soft if it did not depend on the graph, and hard if it depends on something you know about the graph. And this depends on something you don't know, so I don't know, does that mean it's very hard?
Well, you're going to find S naught, right?
Yes.
And you're going to give the method of proof before you figure out what the theorem should be.
Yes, I don't know what the theorem is yet, but that will come out. I mean, after I have proved the theorem, I will know what the theorem is.
Right.
But I have to prove it first before
Right.
I know. So I tried to investigate a smallest counterexample. I want to do deletion contraction. And the smallest counterexample must have the following properties. It must have a Hamiltonian path, because the conclusion here says that it has no Hamiltonian path, and if you have a counterexample to that, there must be a Hamiltonian path. So that's the first property. The second property is that it has connectivity precisely 2. You can delete 2 vertices and make it disconnected. And the reason for this is the following. If it only has connectivity 1, you can break it up and use induction. And if it has connectivity 3, you can delete an edge or contract an edge, you can do deletion contraction. So therefore, the connectivity is only 2, it's precisely 2. It has 2 separating vertices, x and y. And then I started investigating those vertices. And it turns out that I could prove the theorem, any theorem of this type, by the way, for any S node, unless you have the following situation. When you take two vertices away, you create precisely three connected components. And those three connected components have a cut vertex separating x and y. So that's the structure. And then after that, I couldn't do more reductions. And I thought this was the end of it, but then something very nice happened, namely that I was able to characterize these graphs. I was able to say precisely what they look like. The graphs I mentioned, the graphs with a Hamiltonian path and with connectivity 2 and with these separation properties, I can say precisely what they look like. They look like the following. You see the Hamiltonian path starting here, going like this. You start here, you can see the Hamiltonian path. So there certainly is a Hamiltonian path. And it also has the separation properties I mentioned, because if you take two vertices away, you see that there are three components. Here is one component, and you have the upper component, and you have the lower component. And the upper component has a cut vertex, namely this one. Is that right? If I take these two, no, this one it is. This vertex separates these two vertices in the upper component. And that's what they look like. So another way of saying this is that since these graphs are the smallest counterexamples to the theorem I was proving, regardless of what theorem it was, then these graphs must be the graphs which have Hamiltonian paths and which have the smallest chromatic roots different from 0 and 1. And I was then able to find the infimum of the chromatic roots of these graphs, and that became that particular number. Now, the number I described and Jackson's and Bill's constant, they are very close together. So there's a tiny little interval where this theorem applies. So it has no practical applications, but as I said, I believe it may have some philosophical interest. Gordon?
So that's the infimum of those chromatic roots, you said, but it's not a chromatic, you said that polynomial was not a chromatic polynomial itself.
That's right. Okay. That's right. Yeah, well, that comes out by some recursion.
So you just keep building towers taller and taller like this?
Yeah, yeah.
That's very much like Gordon's construction.
Okay.
So another way of describing your construction is you start with K tray.
Yes.
And you choose a Hamilton path, and then you do the diamond reversement on the first edge and the last edge of the Hamilton path.
Is that
and then
one?
you keep on doing it recursively.
The construction you showed us. But you had a lot of words of degree 2, didn't you? Wasn't your construction something like this? I mean, you replace an edge by a 4
Yes.
cycle.
Well, you do that, but you only do it to the first and last edge in the Hamilton path.
I see. Yes, yes. That's right. That's right.
Actually, this is
Yes.
exactly the Hamiltonian graph constructed by Bill Jackson's family graph by the double subdivision.
Are you saying that these graphs are also among your graphs?
No, for my graphs, I have to do it everywhere.
I see. I
For
see.
your graph,
Okay.
you restrict to the first edge and the last edge of Hamilton path.
Okay. So it's your construction, but just applied in a slightly different way.
Your one is a special one. It's those graph with Hamiltonian path.
Yes. Okay. They must be different because you go down all the way to 32/27, and I go down to something higher. So
Yes, it's different.
Yes.
but because I do it everywhere.
that's
and
true.
you do it only on very special edges.
True. Yes. Oh, that's interesting. That's interesting. Yes, that's a nice remark. I would like also to think of Hamiltonian cycles. I mean, this is a theorem about Hamiltonian paths, and if we make it for Hamiltonian cycles, maybe we can get a bigger interval, and that might be a nicer theorem. And that leads to the conjecture which I call the Hamiltonian root conjecture. I believe that if the chromatic polynomial has a root in the open interval between 1 and 2, then there is no Hamiltonian cycle. And this might have a little bit of application. Look, for example, at this graph. Suppose you want to prove that it has no Hamiltonian cycle. It's easy to compute the chromatic polynomial, and this thing here has a root if you put lambda equal to 1, you get something negative. If you put lambda equal to 2, you get something positive, and therefore there is a root between 1 and 2 by continuity. So this graph's chromatic polynomial has a root between 1 and 2, and therefore, if this is true, we have a proof that this has no Hamiltonian path, a kind of certificate. It doesn't qualify for being a certificate because you can't compute the chromatic polynomial in polynomial time, but if Geoff gives me the chromatic polynomial as he suggested, then we have, for a much larger class of graphs, a way of proving that it has no Hamiltonian cycle. But only in the interval between 1 and 2, because already in the interval between 2 and 3, this will become wrong. Here is an equivalent version of the Hamiltonian root conjecture. To say that there are no roots between 1 and 2, actually it turns out to be the same as saying this, because we know what the sign of the polynomial is very close to 1. Bill told us a formula for that. So if there are no roots, then that sign will be the same all the way between 1 and 2, and this is another way of proving it. And this invites to deletion contraction, and to the following conjecture, which I call the Hamiltonian reduction conjecture. This is a dangerous conjecture, but it has been now, I have made it many years ago now, so every time I mention it, I dare say it a little louder each time. So you have a 3-connected graph, it has a Hamiltonian cycle. Then I conjecture that you can find an edge E with the property that if you delete that edge, you still have a Hamiltonian cycle, and if you contract it, you still have a Hamiltonian cycle. And that will imply the Hamiltonian root conjecture, because one can show that in the previous conjecture, a smallest counterexample must be 3-connected, and that's what I am assuming here. So that will prove the Hamiltonian root conjecture just by deletion contraction. And this one has nothing to do with chromatic polynomials. This is purely Hamiltonian cycles. And how can we attack this conjecture? Well, here is a way of attacking it. The following observation is useful. Suppose that you have, well, maybe I should say that if you have a Hamiltonian cycle in a 3-connected graph, of course you can easily delete an edge and still have a Hamiltonian cycle. You can just delete an edge outside the Hamiltonian cycle. You can also contract an edge, namely an edge inside the Hamiltonian cycle, and you will still have a Hamiltonian cycle. But the problem is that you want to do both. And this can be done if a graph has 2 distinct Hamiltonian cycles. Then it satisfies the Hamiltonian reduction conjecture. And the proof is easy, because look at the 2 Hamiltonian cycles. They are not the same. So one of them has an edge which is not in the other. Look at that edge. If you delete that edge, you don't destroy the other Hamiltonian cycle. And if you contract it, you preserve the Hamiltonian cycle C2. So if you have 2 Hamiltonian cycles, you can find that edge just by taking an edge in one of the Hamiltonian cycles and not the other. So this suddenly makes the following question interesting. If you have a Hamiltonian cycle in a graph, can you find another Hamiltonian cycle? The problem is NP hard, NP complete, but there are results on this. Here is a classical result which was invented, I think, in order to attack the 4-color problem, to prove Tate's conjecture. I don't know if Tate's conjecture was disproved in those days. This is an old theorem. If you take a cubic graph, this is a graph where all vertices have degree 3, and you take any edge in that graph, then the number of Hamiltonian cycles going through that edge is even. There will always be an even number of Hamiltonian cycles going through any particular edge. And unfortunately, it has to be mentioned here that 0 is an even number. So the number of you cannot be sure that there are Hamiltonian cycles, unfortunately. It would be much nicer if you could say odd here, then you would have the 4-color theorem, but you can't change the truth. As a corollary, every cubic graph has at least 3 Hamiltonian cycles, and that's best possible. And I should finish soon. There are infinitely many cubic 3-connected graphs which have precisely 3 Hamiltonian cycles. You can start with this graph, the graph of the tetrahedron, and then you can use this operation. Geometrically, you chop corners off the tetrahedron successively. And the number of Hamiltonian cycles will not increase very much. It'll stay 3. But what about graphs which have a little higher connectivity? If you take a Hamiltonian cubic cyclically 4-edge connected graph on n vertices, does it then have at least 100 Hamiltonian cycles if n is large? And maybe I should say what this word means, cyclically 4-edge connected. It just means that if you want to disconnect your cubic graphs by taking away edges, by taking away 3 edges, the only way you can do it is by taking away 3 edges incident with the same vertex. If you have a cubic graph and you take away those 3 edges, you make the graph disconnected. And if that's the only way you can make it disconnected by deleting 3 edges, we call it cyclically 4-edge connected. Does such a graph have at least 100 Hamiltonian cycles if it has 1? And if the answer is yes, you can go even further. Does it have exponentially many Hamiltonian cycles? We don't know. I would like to mention that there is an analogous question of Lobas on cubic graphs for perfect matchings. If you take a cubic graph on n vertices with the property that every edge is contained in a perfect matching, and we have heard about perfect matchings last week, does it then contain exponentially many perfect matchings? This is open. For bipartite graphs it's true, but that's deep. That's the proof of van der Waerden's conjecture. But for non-bipartite graphs it's open. Yeah, I think I should finish soon. Maybe I can finish with some unsolved problems. Suppose you have a graph which has a Hamiltonian cycle. Excuse me. I seem to have lost my voice. Suppose you have a graph with a Hamiltonian cycle, and suppose that the minimum degree is large. So the degree of a vertex is the number of edges going out from it. If that is large, does it then have many Hamiltonian cycles? We don't know. We can also ask it for regular graphs. If you have a regular graph, this means that all vertices have precisely degree r, and if r is large, does it then have many Hamiltonian cycles? If it just has 1, I mean, these conditions do not guarantee 1 Hamiltonian cycle, but if there is 1, this is what we mean by Hamiltonian. Can we then find others? And here is a more specific question. If the minimum degree is at least 10 to the 10, can we find a second Hamiltonian cycle? We don't know. And then this beautiful conjecture of Sheehan, if the graph is 4 regular and there is a Hamiltonian cycle, can we find another Hamiltonian cycle? This has been open for over 30 years. And I proved that if the graph is 100 regular or more than 100 regular, then the answer is true. And that has recently been pushed down to, I think, 28. Something, 22, actually 22. So if we write 22 instead of 4 here, it's true by a recent result by Haxel, Simeone and Verstraete. And let me just mention let this be the last transparency. For bipartite graphs, many of these questions can be answered in the affirmative. If you have minimum degree d in a bipartite graph, then there will be many. In a bipartite Hamiltonian graph, then there will be many Hamiltonian cycles. And there is also a result for girth. If the girth is g and the minimum degree is at least 4, then there are exponentially many Hamiltonian cycles. So if you have a graph just with a modest minimum degree condition, if you exclude all small cycles and you can find just 1 Hamiltonian cycle, then there will be many Hamiltonian cycles. So let me finish here. Thank you very much. Yes, Gordon.
You know only 3 connected graphs with 2 Hamiltonian cycles.
3 connected graphs with precisely 2?
Yep.
Oh, I know some with precisely 1. There are 3 connected graphs with precisely 1 Hamiltonian cycle. But with precisely 2, that's, I don't know. I would think they exist.
So why is that not a counterexample to your conjecture that there's always an edge you can delete and contract?
Oh, because my conjecture doesn't say that a 3-connected Hamiltonian cycle has another Hamiltonian cycle. That's not what it says.
No.
It just says it has an edge which you can contract and delete and still preserve Hamiltonicity. For example, if you have a cycle, maybe I can draw on the blackboard. If you have a cycle of length n minus 1, so you have a Hamiltonian cycle with n vertices, and then you have a cycle with n minus 1 vertices. This is not a second Hamiltonian cycle, but if you have such one, then you will have an edge whose deletion and contraction results in a Hamiltonian graph, because what you do is the following. This vertex is x, so it's over here, and these 2 vertices x and y, they will be somewhere here. Z and y. And let's see, then I just, then I let this, the graph is 3 connected, so there will be a 3rd edge here, and I let that edge be my edge E. If you delete this edge, you still have this Hamiltonian cycle. And if you contract it, then suddenly this becomes a Hamiltonian cycle. So my conjecture says that either you have, if you have a Hamiltonian graph which is 3 connected, then either you have a second Hamiltonian cycle, or you have a cycle going through all vertices except 1. And that's a little weaker than saying that there is a second Hamiltonian cycle. And those which we know of, which only have 1 Hamiltonian cycle, they will have a cycle of length n minus 1. So in the bipartite graph, you cannot have this. But my conjecture is true for bipartite graphs. I mean, I can prove it for bipartite graphs.
Are there a family of Hamiltonian graphs for which your conjecture about no chromatic zeros in 1, 2 is true? Can you prove it for a family of Hamiltonian graphs?
Yes, for chordal graphs, for example. Chordal graphs are graphs which you start with a complete graph and then you add a vertex and join it to a complete subgraph, and if you continue joining to a complete subgraph, then we get what we call a chordal graph. And all the roots of the chordal graphs are natural numbers. 0 and natural numbers.
So that's too easy.
That's too easy, yes. Okay, so one which is slightly more
I mean,
difficult.
for instance, you can prove the Hamilton cycle conjecture for bipartite graphs, but I guess you cannot prove.
That's right. That's right. I thought actually that when I had done it for bipartite graphs, I thought I would come close to your conjecture that if you have a 3-connected non-bipartite graph, it can have no chromatic roots between 1 and 2. And your conjecture implies my Hamiltonian root conjecture. But then Gordon Royle disproved that conjecture. So
Feng Ming has a huge class of graphs that he can prove are that may be Hamiltonian that have no roots in 1, 2.
okay, so that's a positive answer to Bill's question.
That's right.
Yes. Okay. Okay. That's good.
Maybe, I mean, I wanted to use the Hamiltonian property as well.
Okay.
But I'm sure Feynman has that as well.
As soon as we answer your questions, you change the question.
Thanks, Carsten.